Have you ever really thought about what happens when you make a phone call? I mean, it feels instant, right? But between you speaking and your friend hearing you, your voice goes on this absolutely incredible, invisible journey. Today, we're going to follow that journey and see how your voice is engineered into a signal that's ready to fly right through the air.
So this is the fundamental puzzle we need to solve. How on earth do you take something as natural and, wavy as a sound wave and turn it into the precise language of computers, a clean stream of ones and zeros? It's a huge challenge, but it's one we've gotten really good at solving.
Okay, so let's put on our systems engineer hats for a minute. The very first problem we face is that the raw analog sound wave from your voice, well, it's just not built for the rough and tumble world of wireless communication. It's fragile, and honestly, it's super inefficient. I mean, think about it. The air around us is crowded. It's filled with radio signals, electrical noise, all sorts of interference. An analog signal gets distorted by all that static so easily. And what's more, sending that full, rich sound wave would be like trying to ship a life-size statue. It's just way too big and bulky for the limited bandwidth we have. We need a much smarter approach.
And that smarter approach, of course, is to go digital. This is the first and maybe the most important part of the whole journey. We're going to convert that messy analog wave into a clean, precise, and really robust digital format. This is where the magic really starts to happen.
This whole transformation breaks down into 4 main steps. First, we'll trim the signal down a bit. Then, we'll measure it thousands of times. After that, we assign numbers to all those measurements. And finally, we package it all up. Let's walk through each one.
First things first, we do some very smart trimming. See, your voice has a whole range of frequencies, but you don't actually need all of them to understand what someone's saying. So we use a filter to chop off everything above 3.4 kilohertz. It's a great first move because it immediately makes our signal smaller and way easier to work with, without you even noticing a difference in clarity.
Next up is sampling. So now that we have our trimmed down wave, we start taking thousands of tiny little snapshots of it every single second. How many? 8,000 times a second, to be exact. Each one of those snapshots measures the height of the wave at that one specific moment in time. What we're left with is a series of dots that perfectly map out its shape.
So what do we do with all those little snapshots? Well, this is where we turn them into actual numbers. It's a process called quantizing. Each sample is given a number based on a scale of possible values. And in the GSM system, that's the global standard for mobile calls, that scale has 8,192 levels. That means every single sample becomes a super precise 13-bit number. And just like that, we've officially turned a wave into a stream of data.
So, we've got our digital signal. Awesome. But our job as engineers isn't over yet, not by a long shot. Now we have to make this data stream as small and as tough as possible for its trip. It's time to get clever with some coding.
Here's a really good way to think about what happens next. The old analog way was like sending a huge, high-resolution photo of your voice. But digital speech coding, that's different. It's like sending a much, much smaller blueprint that gives the other phone the exact instructions on how to rebuild your voice perfectly on its end. And how good is this blueprint method? Well, look at this. It achieves an incredible 8-to-1 compression ratio. We are squeezing the data down to 1/8 of its original size. That is a massive, massive efficiency gain. It's what allows so many more calls to share the same airwaves.
The result of all that compression is a really lean data stream. Our signal is now cruising along at just 13 kilobits per second. So, we've made it small, now we have to make it strong.
And to make it strong, we use something called channel coding. Basically, we add some extra redundant bits into the data stream. Now, this isn't just wasted space. Think of it like protective armor, or maybe packing peanuts. It's a built-in repair kit that lets the phone on the other end detect and even fix errors that happen along the way.
Now, you're probably thinking, wait, aren't we just making the data bigger again? And yeah, you're absolutely right. The bitrate goes up from 13 to 22.8 kilobits per second. But this is a super important trade-off. We're giving up a little bit of that small size for a huge increase in reliability. It's what keeps your call from getting all garbled or, just dropping completely.
Our signal is now small and it's protected. But we are not done. We have 2 more really ingenious tricks up our sleeve to bulletproof these bits against both corruption from noise and, well, from nosy eavesdroppers.
This next idea is one of my favorites. It's called interleaving, and it protects against something called burst errors. That's when a whole chunk of data gets wiped out at once. By literally scrambling the order of the bits before we send them and then putting them back in order on the other side, any damage gets spread out. It turns one huge fatal error into a bunch of tiny fixable ones. It's just genius.
Okay, reliability is one thing, but privacy is something else entirely. The next step is to make absolutely sure that nobody can listen in on your conversation, and for that, we use ciphering.
Think of this as a secret decoder ring for your phone. Using a standard encryption algorithm called A5 and a secret key, the entire data stream gets completely scrambled into what we call ciphered text. It is total gibberish to anyone who doesn't have the exact same key to unlock it on the other side.
Okay, we're in the home stretch now. The data that represents your voice is now small, it's error protected, and it's securely encrypted. There's just one last thing we have to do before we can launch it into the air as a radio wave.
And that final step is called modulation. The easiest way to picture this is to think of our digital signal, all those ones and zeros, as a letter. You can't just throw a letter into the wind and hope it gets there, right? You need an envelope. The radio wave is that envelope, our carrier. Modulation is simply the process of putting our signal onto that carrier wave.
And naturally, we're not using just any old envelope. The GSM standard uses a really sophisticated and efficient method called GMSK. The big advantages are that it crams a lot of data into a small amount of bandwidth, and, something we can all appreciate, it's very gentle on your phone's battery. And there you have it. The journey is complete. The sound of your voice, filtered, sampled, digitized, compressed, armored, and encrypted, is now a modulated radio signal, finally ready to start its actual physical journey through the air at the speed of light.
It is just a staggering amount of engineering packed into a fraction of a second. It really makes you wonder, doesn't it? What other simple, everyday technologies that we all take for granted are hiding this same level of mind-bending complexity, all working perfectly